Okay, practice problems. Number one, a 490 Newton object is suspended from a rope. So we got an object. We've got um, it's going to be 490 newtons downward, and it's asking how much force upward is going to be required here. And the key bit here that you might have not seen is that it says that it's raised vertically at 5 meters per second, not 5 meters per second squared. It's not accelerating, which means that there's no force, right? Things in motion just stay in motion. So this thing isn't accelerating. That means these two forces are balanced. So if it's 490 down, it has to be 490 newtons up to keep this thing moving at a constant velocity. Forces need to be balanced. Okay, B. What is the force required to accelerate it down at 3 meters per second squared? So now I can kind of look back at my old, or I'll make a new drawing. Let's make a new one. All right, so we still got 490 going down. And I know that it's accelerating downwards, so this arrow on the bottom is going to be longer. So I'm going to make this one, I don't know, somewhere in there. Some kind of arrow like that, right? And I got to figure out what this is. So I got to figure out what FT is. Now what we're going to do is we got to make our formula, right? Our formula is F net is equal to Ft plus Fg. So far I'm good for Fg, right? It tells me Fg is 490, so I'm good for that one. Do I know, and I'm looking for force tension, right? That's going to be the force that I'm going to have to be pulling upward with, right? Do I know F net? Shouldn't have put a check mark yet. Do I know F net? I do know that it's 490 newtons down, right? So I can figure out F net by figuring out our mass first, right? Because I can use this to figure out our mass. So I can go mass is going to be equal to Fg over G. So that's going to be equal to 490 newtons divided by 9.81 meters per second squared. So M is going to be 49.95 kilograms. Okay, so I'm good for that. I know my acceleration now. So what I'm going to do is just keep working my way down with this formula. So F net, I'm going to rewrite that as just mass times acceleration. That mass is this. The mass didn't change, right? So the mass that I found there, that is this mass. Acceleration, that's the one I have in the problem here. And it's going to be down at that, so it's going to be negative when I put that 3 in there. So I'm going to say that's equal to Ft is still there. Fg, I could put the number in if I actually wanted to now. I'll put it in next time. So say that's Fg. So that's going to be those vectors still. Acceleration is the vector part of that. Yeah, so we could put our numbers in now or rearrange it. Let's just rearrange it first. So I'll say mass times acceleration minus Fg is equal to Ft. And then filling stuff in here, I know the mass is 49.95 kilograms. Acceleration is negative 3.00 meters per second squared. And then minus, and it's also going to be negative, right? Because it's 490 down. So minus negative 490 newtons is equal to Ft. And then finally I get, it's 340 newtons is equal to Ft. So that's the tension force that's going to be required to keep this thing accelerating downward at negative 3 meters per second squared. Okay. Now, this one. A 20 kilogram mass is placed on a 50 degree incline. If the coefficient of friction is 0.35, what is the acceleration of the mass? This is going to be really important that we make a good free body diagram on these. So make your dot. Gravity is always going to be pulling straight down, and what I would recommend too is make gravity pulling straight down pretty long, because we've got to make a triangle out of this, right? So that's going to be FG. And Fn, remember, and this is the key bit, it's going to be going off perpendicular to the slope. So Fn is going to be on an angle like that. And maybe, I'm going to make this a different color. Let's make that red. Okay, so Fn is going off on an angle like that. And it should have been longer. Let's make it a little longer. Okay. Now, where are other forces? Can we put any other thing on here? So we know that it's going to have a coefficient of friction. So I know that this force of gravity, if you think about it, if you just left this alone, it would slide down, right? If the coefficient of friction was small enough. So there's a force going down the ramp. That means there's going to be a force also going up the ramp here. But we don't know what it is. We don't know if that force is going to be like, bigger or smaller than the other one. So the force applied here is going up. So we got that one. And that's pretty much it, right? That's going to be our forces. Ooh, actually, I kind of misspoke. So what's going to happen here is same type of thing. You're going to have this going up. We're not pulling it up the ramp, though. I was thinking we were pulling it for some reason. What's going to happen is that we're going to have a force of friction going up the ramp, because if you left this thing alone, right, it's going to want to slide down the ramp, right? Friction's going to be the thing that's wanting to keep it stuck to the ramp. So we're going to have a force of friction going up. So, yeah, my bad. Okay, so that's it. That's our forces that we got going on here, right? We are going to call this way, positive and negative. And we're going to call this way positive and that negative. So we're on that tilt there now, right? We just kind of made what we're calling positive and negative different now. So what you're going to do now is split this force of gravity into its components, because now that we've called our positives and negatives on the same as the slope, force of gravity isn't complying. So we need to split it up. So going down here, you're going to have the y component of gravity. So F, and maybe I'll go FGY. FGY. And this side, I'm going to have FGX. Okay, and then the other bit of info there was that this too was going to be 50 degrees. So now using your trigonometry, well, actually, now, before I do that, let's figure out what FG is. That's going to make things easier. So I'm going to go, okay, FG is going to be equal to mg. So FG is going to be equal to 20 kilograms times 9.81 meters per second squared. So FG is equal to 196.2 newtons. Okay, so now that I know that, that'll make things a little easier here. So let's split this into its components now. So FGX, this one, is going to be 196.2 times sine, because it's on the opposite side, sine 50 degrees. So that's going to be 150.298. I'll leave a bunch of decimals. Newtons. Okay, let's now figure out the other part of it. So the red one here. So FG in the y direction is going to be 196.2 2 times sine 50. Oh no, cosine 50. That dot there means times. Times cosine 50 degrees. That's going to be 126.115 newtons. All right, so we're getting there. Okay, so now that I got those numbers, let's just kind of think about what we're doing here. FGX, this one here, that's the force that's pulling this block down, right? Even though this vector is like, down below it, remember you can move vectors around. This vector is that way, it's pulling to the left. That means that it's pulling this box down the ramp. Okay, so that's what we have going on. We got to figure out what the force of friction is that's trying to stop it from going down the ramp. And the only way we can figure out the force of friction is if we know what the normal force is. And the normal force is equal to that number that we just found, right? They're balancing each other there. So I'm going to write up here, FGY is equal to, let's do magnitude, FGY, just so we're clear. The magnitude of that is equal to the magnitude of Fn. So then I'm going to say, therefore, that means therefore, those dots. Fn is going to be equal to 126.115 newtons. Now we have a formula, right, for force of friction. Force of friction is going to be equal to mu times Fn. So the force of friction in this case is going to be the coefficient of friction up there, so 0.35 times 126.115 newtons. So the force of friction is 44.14 newtons. Okay, we're getting there. So, I should have made that green. It was green up here. So that's the force of friction. Now we have two forces. We got the force of friction going along the x-axis, or the x-plane that we're calling it, and we have the force of gravity in the x-plane. We got to figure out the net result of those two. So if we do that, we're going to say F net is going to be equal to Fg in the x direction plus force of friction. And it's going to be really the vectors of those. So F net is going to be, 150.298. We called that negative, right? So that's going to be negative 150.298. It's going down the slope, right? Plus our force of friction. So 44.14 newtons. So F net's going to be 106.158, and it'd be negative, right? It's going down the ramp is all that really means, newtons. Okay, we're almost there, I promise. Now, what's the acceleration? Well, we know the mass now, right? So acceleration is equal to F net over mass. So the acceleration is going to be 106.158 newtons divided by the mass of, what did I say? 20 newtons? Oh, 20 newtons, 20 kilograms. Mass isn't in newtons. 20 kilograms. So acceleration is negative 5.3 meters per second squared. So that means it's accelerating down the ramp at 5.3 meters per second squared. And yeah, that should have been 5.3, not 5.31, because of this number. And this probably should have said like down the ramp or something like that, right? Okay. So that's where we're at. So go ahead and do the hand-in assignment now. You've seen ones like this before, right? So go ahead and, yeah, draw your free body diagrams and do a whole bunch of these questions. So that's it for that video.